as it was said, so the topic of this talk will be, so we'll look at the question of studying the spectrum of random quantum channels. So quantum channels, as we will explain later, are described like transformations of open quantum systems. And we will be interested in like studying their spectrum. And in fact, to be a bit more honest, I've realized when preparing the talk that in the end I will probably have time only to talk about the question of studying the spectral gap of these objects, so the gap between their largest and second largest eigenvalues. Okay, and it will be like very much of an overview talk. I mean, I will be talking about a lot of results that are not mine at all. And the two results of mine that I will be mentioning are from these two papers. So this quite old paper with David Perez Garcia, where we looked at a very specific model of random quantum channel, studied its spectral gap, and where our motivation was really to look more at implications of this result when studying many body quantum systems. So I will try to mention this at the very end of my talk. And then this more recent paper with Pierre Youssef, where this time it was much more of a mathematical paper, trying to really look in the most general way possible somehow, what can we say about the spectral gap of random quantum channels. Okay, so let's get started. So first I would like to try and motivate why it's actually interesting to look at this question of the spectral gap of quantum channels. And for this, I will go back a bit to the classical setting and explain that it's for the exact same reason as people have been studying the spectral gap of graphs, or if you want, of transition matrices associated to graphs. And this will bring us to defining these notions of, like both classically and quantumly, of expanders. So let's get started. So in the classical setting, so we are looking at some finite graph G that is on n vertices, and that has the property of being what I call d biregular. So what I mean by this is that each vertex of my graph has exactly d incoming and d outgoing edges, okay? So, I mean, with this definition, I'm kind of implying that my graph is directed. The undirected case is simply corresponding to the case where you have to see like each non-directed edge as a double edge with like one incoming and one outgoing. So actually I've realized just during the break that maybe I should have drawn a picture, so I've done it here. So here you have an example of what I'm saying. So you have a graph G on 4 vertices, and with this degree d of this incoming and outgoing degree, which is equal to 2. And then one object that will be really important for us later is the adjacency matrix associated to this graph that I have actually normalized so that it's a transition matrix. So this adjacency matrix, it's an n times n matrix A, whose entry KL is simply the number of edges from vertex L to vertex K divided by D, so the total number of edges that arrive in vertex K. Okay, so that's this, it's a bistochastic matrix by this property of being having a biregular graph. So it's a bistochastic matrix that sends probability vectors on probability vectors. So now we will denote by, so here you have again, like in this example, what this matrix A looks like. Okay, so now we will denote by lambda 1 of A to lambda n of A the eigenvalues of this matrix A that I will order in non-increasing modulus. So just one remark here. So here in the case where my graph G is undirected, then this matrix A is symmetric and these eigenvalues are real, but in general they're not. And especially for the purpose of this conference. Okay, so now the property that G is biregular, what it implies is that the largest eigenvalue of this adjacency matrix A is always going to be equal to 1, and with associated eigenvector, this uniform probability vector U, which has like a coefficient 1 over n in each of its entries. And now what we will define as being the spectral expansion parameter of this graph G is simply the second largest eigenvalue of this adjacency matrix A. So maybe one like very easy but important observation for what follows is that this parameter lambda of G, so the spectral expansion parameter, another way of seeing it is as simply being the largest eigenvalue of the matrix A minus J, where J is the adjacency matrix of the complete graph on n vertices. So the matrix that has all its entries equal to 1 over n. And indeed, this matrix J, it's a matrix that has one eigenvalue equal to 1 associated to this uniform probability vector U, and then all the rest equal to 0. Okay, so looking at the second largest eigenvalue of A is really just looking at the largest eigenvalue of A minus the projection onto its leading eigenvector. And so we see from this that this parameter lambda of j somehow is a distance measure between our graph of interest G and this complete graph on n vertices, which is defined through a distance on the corresponding adjacency matrices. And now we can define in a kind of informal way, a bit more of a physics way than a math way, what we will call a classical expander, so an expander graph. So it's a graph G on n vertices, that is D biregular, and that combines the following two properties. So on the one hand, you have that this graph is sparse, so its degree D is very small compared to n, compared to the degree of this complete graph, for instance. But on the same time, you want it to be very expanding. And this means that this spectral expansion parameter lambda of G is very small compared to 1. So you want this graph to have a large spectral gap between its largest eigenvalue 1 and its second largest eigenvalue. And so why is this object interesting? Well, it's simply because somehow you can view an expander graph as being an economical approximation of this complete graph. So it's economical because it's very sparse. It has a very small degree, very few edges overall. But it's still close to the complete graph from this spectral closeness definition. And in particular, one interesting property that such a graph will have is that if you look at a random walk that is supported on such a graph G, it will converge very fast to equilibrium. So it's the equilibrium here, the fixed point of our dynamics is this uniform probability vector U. And if you start from any other probability P on your n vertices, so any distribution on your graph, and you apply your transition matrix A like a repeated number of times, you're going to converge towards this uniform probability distribution, and the speed of convergence is going to be exponentially fast, and where the rate of this exponential convergence will be higher if your spectral expansion parameter is smaller. Okay, so this having a small spectral expansion parameter is really quantifying how fast you're converging towards equilibrium. So you have a graph again that is sparse, but still mixing very fast. So that's really the interest of this kind of objects. Okay, so that's for the classical setting. So now let's try and understand what we can do, in a quantum setting. So how can we translate this in the quantum world? So if you want the kind of classical quantum correspondence in this case goes as follows. So before we were talking about probability vectors P in Rn. Now the quantum equivalent of this are going to be density operators, so n times n complex matrices that have the property of being self-adjoint, positive semi-definite, and with trace 1. So this kind of density operator rho, you can really view it as, so if you look at its eigenvalues, it's a probability vector. There are non-negative and summing up to 1. And then you have this extra freedom in this quantum setting of choosing in which basis your density operator is actually diagonal. So that's why I'm saying it's this quantum generalizations of classical probability distributions. Then before we were looking at transition matrices A that were mapping probability vectors to probability vectors. Now in this quantum setting, the equivalent of this are going to be what we call quantum channels. So these are linear maps from the set of n times n matrices to the set of n times n matrices that have two properties. So first you want them to preserve the trace, and you want them to be completely positive. So what it means is that they send, such a map sends a positive semi-definite matrix on a positive semi-definite matrix. And this property actually remains true even if you tensor your linear map phi with the identity on some auxiliary Hilbert space. So that's, again, I don't want to enter in too much details about this, but just to say, so the equivalent in this quantum setting of transition matrices are these completely positive and trace preserving maps that map density operators to density operators. And now, final thing, before in our classical case, we were looking at graphs that were biregular, which, as we said, at the level of the corresponding adjacency matrix, what it means was that this matrix was bistochastic. So its fixed point was this uniform probability distribution. Now, in the quantum case, it will correspond to having our quantum channel phi that will leave the equivalent of the uniform probability distribution, which is what in the quantum jargon is sometimes called the maximally mixed state. So it's just the identity divided by the dimension. So we will want that our quantum channels has this as fixed point, has this maximally mixed state, so this identity as fixed point, which means that our map is what we call unital, like when it fixes the identity. Okay, so with this, now we see, so what is the, if you want, the quantum analog of the transition matrix associated to a biregular graph? it's simply a unitole quantum channel. So now, one thing I haven't yet answered is, what would be the analog of the degree in this quantum picture? So what would measure somehow the sparsity of our quantum channel? And the answer that I am going to give is that the analog of the degree in the quantum setting is what we call the cross rank of our quantum channel. So let me explain what it is. So it's known that if you have a completely positive map on n times n matrices, you can always describe its action in the following way. So you say that, so your map phi, it will send any input matrix X on something which will be a sum over I of conjugations by some matrices Ki. Okay, so you always have a writing of this form for a completely positive map. And where these operators here, these operators Ki, are called the cross operators of our completely positive map phi. And we will define the cross rank as being the minimal D here in the sum, such that you can actually write the action of phi under this form. Okay, there is a lot of freedom in like this writing. You have many different ways of writing it. And the minimal D such that you can actually describe the action of phi in this way is what we're going to call the cross rank of our completely positive map. And just a remark is that if you have a map that is acting on n times n matrices, this cross rank is always at most n squared. You can write any completely positive map on n times n matrices in this way with n square elements in this sum. And so a quantum channel that is sparse is going to be a quantum channel where this cross rank D is much smaller somehow than n squared. And just one final comment, because it will be useful for us later. So on this writing here, you can read the conditions of preserving the trace or being unitole at the level of these cross operators by the following normalization conditions. So our CP map phi is going to be trace preserving if and only if the sum over I of the Ki star Ki is equal to the identity. And in a dual way, it's going to be unitole if and only if the sum over I of the Ki star is equal to the identity. Okay, so that's how we see this trace preserving and unitole conditions on this cross decomposition. Okay, so now why do I claim that somehow the quantum analog of the degree would be this cross rank? So one kind of handy, like hand-wavy way of justifying this is by saying that somehow these two quantities quantify more or less the same thing, namely how much your dynamics can spread in one iteration. So indeed, so if you have G, a graph with degree D, and say you start from a probability distribution on your graph, which is a Dirac mass. So it's supported only on one of your vertices. So the cardinality of its support is 1. And then you apply your transition matrix A just once. Then if your graph has degree D, the support of this resulting probability distribution will have at most cardinality D. There's at most D vertices that you can attain in one iteration of your dynamics. And it's exactly the same that happens in the quantum case, that if you start from a density operator that has rank 1, so it's a rank 1 projector onto one given direction, and you apply your quantum channel phi that has cross rank D once to it, then the rank of this operator is going to be at most D. So that's why I'm saying like somehow these two quantities, the degree and the cross rank, are really quantifying the same notion. But we will see later some more mathematical statements that show that indeed these two things are really corresponding to one another. Okay, so now that we have this, we can define what is going to be a quantum expander, just as we defined what was a classical expander. So we have a phi, a unitole quantum channel on n times n matrices that has cross rank D. We denote by lambda 1 to lambda n square its eigenvalues that we order in a non-increasing modulus. As we've just explained, the fact that phi is unitole, it implies that its largest eigenvalue is equal to 1, and with associated eigenstate, this maximally mixed state, so this identity over n. And we will define its spectral expansion parameter as being simply its second largest eigenvalue. Again, we can, exactly as in the classical case, view this spectral expansion parameter as a parameter that measures the distance of our quantum channel to a specific quantum channel, and namely this channel that I've denoted with a pi and that I've called the maximally mixing channel, and it's the channel that sends everything onto the maximally mixed state. So it's the channel that sends everything onto the identity. So yeah, so this spectral expansion, so the smaller the spectral expansion parameter, the closer our quantum channel to this maximally mixing channel pi. And again, so the kind of informal definition of what a quantum expander is. So it's a unital quantum channel phi on n times n matrices that has cross rank D, and which combines the following two properties. So on the one hand, it's sparse, so its cross rank is very small compared to n squared, which, by the way, is, so this maximally mixing channel, if you want to describe its action, you will need n squared cross operators. It has a maximal cross rank. So, oops, sorry. So you have this, sparse, so you have the sparse quantum channel, but you want it to be spectrally expanding, so you want this, that it has a large spectral gap between its largest and second largest eigenvalue. And exactly as in the classical case, we will have that if you have such an object, so it's a graph that is economical, but resembling this maximally mixing channel, and in particular, if you have if you look at the dynamics associated to this quantum channel, it's going to converge very fast to its equilibrium, which is this maximally mixed state. And with, again, the speed of convergence that is upper bounded by, so square root of n times this spectral expansion parameter lambda to the power q. Okay, so now that we have seen a bit these definitions, I would like to move on to the core of my talk, which is, so what we're going to see is that actually both in the classical case and in the quantum case, if we look at random graphs or random quantum channels, they actually provide examples of very good expanders. So they have this property that they have a very large spectral gap with high probability between their largest and second largest eigenvalue. So that's what we are going to see next. So first, let me recall, very briefly what is known in the classical case. I'm not a specialist at all about spectral gaps of graphs, but just somehow it's giving us an idea. Then because in the classical case, it's been studied much more, and somehow it's giving us an idea of what we can hope for, like in the quantum setting, like what kind of results we may hope to reproduce or not. So for this overview of what's known in the classical case, I will focus on the case of undirected graph, so the case where this associated adjacency matrix A is symmetric. So, but I promise it's the only slide that I focus only on the symmetric case. Afterwards, in the quantum case, I will really talk about objects that are not self-adjoint. Okay, so it's known classically that, so we have actually a lower bound on how expanding a given graph can be. And this lower bound is the following. So we know that if we have a graph on n vertices that is d-regular, then its spectral expansion parameter is always larger than this value here, so 2 times square root of d minus 1 over d, minus a quantity that vanishes as n grows. So this is somehow the best we can achieve, is this value here for the second largest eigenvalue of the adjacency matrix associated with a graph that has degree d. And so people in the classical graph theory have called Ramanujan graphs that would achieve this lower bound, so that will be such that their spectral expansion parameter is this optimal value 2 times square root of d minus 1 over d. And of course, obvious question is so do such graphs exist? And so it's been a very long line of research to try and understand whether they do. So first, people provided more and more explicit constructions of such Ramanujan graphs, but only for specific degrees. So when the degree was a prime power plus 1, they had algebraic constructions to exhibit examples of graphs with this property. And then it's also been shown, and this I will come back on it in a minute, because it's really what the core of what is going to be interesting to us, that if you construct your graph at random, then they will be almost Ramanujan, so almost achieving this bound here for all degree d. And finally, it was also shown in a breakthrough results from a bit less than 10 years ago that in fact, exactly Ramanujan graphs exist for all degree d, even if we're not able to actually exhibit an explicit construction. Okay, so let me just comment a bit more on this second point about random construction. So what has been shown is that, in fact, if you want, when n is large, then in a way, almost all regular graphs are almost Ramanujan. And this is the statement in the following theorem, which was initially due to Friedman. So if you fix, imagine that you fix your degree d, and then you pick g, a graph that is uniformly distributed on the set of all possible d-regular graphs on n vertices. Okay, so there is a way of defining this abstract measure, so this uniform distribution on the set of all d-regular graphs. Then what you can show is that for any error epsilon that you fix, when n becomes large, then with probability going to 1, the spectral expansion parameter of your random graph G is going to be smaller than this optimal value, 2 times square root of d minus 1 over d, plus this fixed error epsilon that you have fixed in advance. Okay, so that's what I mean when I say that for large n, almost all regular graphs, according to this, like when they are distributed according to this uniform distribution on the set of all d regular graphs, are going to be almost Ramanujan, so achieving this optimal bound up to the small error epsilon. So one remark, because it's going to be interesting, I mean, it's going to be useful for us on the next slide when we're going to talk about what is known in the quantum case, that initially this result was not proven directly for this like abstract measure on the, like this uniform measure on the set of all d regular graphs, but for a much simpler and much more concrete model of random graph, which is the so-called permutation model. So it's a very simple model that you can describe as follows. So when d is even, you say, okay, so let's pick sigma 1 to sigma d over 2 permutations of n element that I pick uniformly distributed and independent from each other. And then I look at the graph G that has as edges, so it has an edge between each vertex k and the vertex sigma I of k, and each vertex k and the vertex sigma I minus 1 of k. So by construction, I have a graph which is d-regular, random, and for this model, it was shown that it satisfies the conclusion of this theorem here. And then it was shown that for large n, you can actually compare this uniform distribution to this very concrete permutation distribution. Okay, so that's one first remark. And then another one is that here in this statement, we are really putting ourselves in the setting where we fix the degree, and the only thing that we let grow to infinity is the size of the graph. And then there's been a lot of research to try and improve this and show that in fact this result holds true even if you allow your degree d to grow with n, so slower than n, but whatever growth rate you put on dn, then this result will remain true up to a constant multiplicative factor, but at least this order of magnitude of 1 over square root of d for the second largest eigenvalue remains true. Okay, so that's basically like a bit like what is known in the classical setting. So now let's try to understand what we can do in the quantum setting. So in the quantum setting, so first there is a kind of similar lower bound on how expanding a quantum channel can be, and it's the lower bound is as follows: that for any unital quantum channel phi on n times n matrices that has cross rank d, its spectral expansion parameter is larger than some constant over square root of d minus a quantity that vanishes as n grows. So here, so the exact constant here, so if we restrict ourselves to looking at self-adjoint quantum channels, then the value is exactly the same as in the classical case, so this 2 times square root of d minus 1 over d. If we go beyond this setting, I mean, there are some known values for the C, but they are not really expected to be tight, the known values. So somehow in what follows, we will consider that we have a quantum channel that is an optimal expander as soon as this order of magnitude 1 over square root of d is satisfied for the spectral expansion parameter. Okay, so that's what we will consider being an optimal quantum expander. And again, you can ask the same question as classically. So do such objects exist? And in fact, so the first attempts that people made at exhibiting like explicit examples of optimal quantum expanders all failed. So the idea was somehow to take inspiration from the like classical setting. So take optimal classical expander and somehow embed them in a quantum setting. And these gave results that were non-trivial, but not achieving this optimal scaling for this spectral gap. And okay, so then you can ask, but maybe if like explicit constructions are I mean, too complicated to exhibit, maybe we can look at random constructions. And that's so that's what people try to do. But of course, so one first question would be, so what would be a natural way of sampling quantum channels at random? Of course, you can, I mean, as classically, you could define like abstractly so there exists a uniform measure on the set of all unital quantum channels with cross rank d. But this is not super easy to attack from a mathematical point of view and to say anything about like objects that follow this distribution. So you could ask, are there some more like concrete and more simple distribution that we could look at? And a natural idea would be like to say, okay, so maybe what we can do is pick the cross operators composing my channel at random. So I pick these matrices K1 to KD at random under the two normalization constraints here that will guarantee that if I look at the associated random CP map, it will be trace preserving and unital. Okay, so that's one thing that you can do. And that's indeed what Matt Hastings did in 2007. And he proved the following result, which, if you want, is really can be seen as the exact analog of this permutation model result in the classical case. So the model he looked at was the following: say, okay, let's fix our cross rank D to be even, and then let's pick a U1 to UD over 2, some unitaries on Mn, so on Cn, that are hard distributed, so uniformly distributed and independent from each other. And then I will look at the quantum channels that has as cross operators, so all the ui over square root of d and their joints, okay, and they're all the ui star over square root of d. So this map was a self-adjoint, and for this one, so he proved the exact same result as in the classical case, namely that for any error epsilon that you fix, when n grows, then with probability going to 1, the spectral expansion parameter of this random unital quantum channel is going to be smaller than 2 times square root of d minus 1 over d plus the small error epsilon. So again, as I told you, so in the particular subset of self-adjoint quantum channels, this bound is the optimal one. I mean, that's the optimal value that you can reach. And then later it was shown by Gilles Pizier with completely different techniques that, in fact, I mean, if you replace this model by a model where you pick all your D hard unitaries independently from each other, so you don't have a map which is self-adjoint anymore, then this result remains true up to potentially a constant multiplicative factor here, but the scaling as 1 over square root of D here for the second largest eigenvalue remains true with a non-self-adjoint model where the cross operators are unitary operators. So, okay, with this result, now we can ask, okay, so how much can we, extend this result? Like, because here we have now, okay, we have one example of an optimal quantum expander, but we're still far from like the variety of results that are known in the classical case, and namely that, yeah, if you take one that is uniformly distributed, then it will be with high probability an optimal classical expander. And this, we're still far from this. And we can ask, so is this distribution that we're looking at somehow close or not to this uniform distribution? And also something else is that in this classical case, we like all the results that I've shown for now were really only in the regime where this cross-rank D was fixed, and the only thing that you make grow to infinity is the dimension of your underlying space. And again, this is a limitation that we would like to overcome. So one difficulty, if you try to think of like faster variety of models of random quantum channels, is that if you want to impose that your CP map phi is at the same time trace preserving and unital, then this is very constraining. I mean, you have to satisfy these two normalization constraints here on your random cross operators, and it's quite constraining. And somehow the only natural thing that you can think about is to take all of these cross operators as being multiples of unitaries, so that indeed, I mean, this is clearly satisfied because for each of these ki star ki or ki star, you have something which is a multiple of the identity. So if you want to get a bit more freedom, somehow you need to relax this assumption of being exactly unital. And indeed, it's quite natural to extend this definition of being an expander to channels that are not exactly unital, but somehow close to unital. And what I mean by this is that they have a fixed point, rho star, which is not necessarily this identity, so this maximally mixed state, the state that has the largest possible entropy, but any state that has a large enough entropy. So here this S is the von Neumann entropy, which is just defined as minus the trace of rho log rho, and like somehow generalizing the Shannon entropy for probability distributions. And somehow the only thing you want to impose is that this entropy of the fixed point is, say, larger than some fraction alpha of the entropy of the maximally mixed state. So, and as soon as you have this, it's actually, it's already somehow interesting to consider the notion of being expanding. And in this new setup now, so this spectral expansion parameter phi, it's not measuring anymore the distance of your channel phi to this maximally mixing channel, but to the channel that sends everything onto this fixed point rho star, which is not necessarily the identity. So it's this map here. And indeed, I mean, in fact, I mean, that's something that's been done also in the classical setting of relaxing this assumption of having like a strictly biregular graph. For example, to look at many natural examples of random graphs that are interesting, like Erdős-Rényi graphs, but that are not exactly biregular, but for which it's still interesting to study their spectral expansion properties. So if we do this, then probably the simplest model that you can think of a random quantum channel. So if we relax this assumption that we need our channel to be exactly unitole, then very, very simple model is to say, okay, so let's pick our cross operators as independent Gaussian matrices. I mean, that's really the most stupid thing that you can do. And so that's a model that we looked at with David Perez Garcia. And so the result is the following. So we said, okay, so let's pick G1 to GD, some independent Gaussian matrices. So what I mean is that each of these matrices has entries that are independent Gaussian entries with mean 0 and variance 1 over n. And then I look at the following cross operators that I denote ki tilde for now because they are not yet my final cross operators, and which are simply these Gaussian matrices Gi renormalized by square root of d. Now, so if I look at the random CP map phi tilde that has this ki tilde as cross operators, it's not exactly trace preserving, but in fact almost by nice concentration properties of Gaussian matrices, we can show that if we look at this sum sigma, which is the sum of the ki tilde star ki tilde, with very high probability, it's going to be very close to the identity. And in particular, it's going to be invertible. So what we can do is define some new cross operators ki, which are simply this ki tilde multiplied by sigma to the power of -1/2. So that by construction, if I look at the map phi that has these new cross operators, it is going to be trace preserving. And for this new random CP map, which is trace preserving, I can prove the following, that with probability going to 1, and in fact we have quantitative estimates, so going to 1 exponentially fast as n goes to infinity, we will have that the entropy of its fixed point is very, very close to the maximal possible value, in fact only up to an additive error, not even a multiplicative one, and its spectral expansion parameter will be smaller than a constant over square root of d, which is the optimal value that we're aiming at obtaining. So the interest of this result is really that, it's really giving you some quantitative estimates of like how far you are from like what is the probability of not satisfying this optimal expansion property. And these estimates are really valid for any d and n that you want. Like you really don't need to have one that is fixed, the other one that grows. It's really a statement that is valid for any large d and n. And finally, just one quick remark. So there's one other model that was studied before the work that we did last year with my colleague Pierre Youssef, which was yet another natural model where this time the cross operators, the random cross operators, were taken as by starting from a big horizometry and then taking blocks of this big horizometry, and that's how this random quantum channel was defined. And also this model was shown to be, when n was large, almost surely an optimal quantum expander. But somehow, so up to like last year, so we had basically the three examples. So with cross operators that were unitaries, with cross operators that were Gaussians, with cross operators that were blocks of a horizometry, and that was it. That's basically the only three examples that we had of optimal quantum expanders. So one question that we asked with Pierre Youssef was to wonder, so okay, like, can there be some kind of more like universal statement that we can make? That's always what you want to try and do in random matrix theory, to say, okay, things that are true for Gaussian matrices, I mean, should be somehow true for much more, much simpler distributions that have some like sufficiently nice properties. So that was the goal of this work. And okay, the result that we proved, I mean, it's the most technical side of my talk, but let me try and get you through it. So, okay, so what we proved is the following. So we started from some matrix A, which has a bistochastic matrix whose second largest eigenvalue is smaller than some constant over square root of d. So for example, this bistochastic matrix could be the adjacency matrix of any classical, optimal classical expander graph. Okay, so if we have a d biregular graph G whose spectral expansion parameter is smaller than something that scales as 1 over square root of d. So we start from, so it could be like an explicit example of a optimal classical expander. And then what we do is, so we pick some random matrix W, complex matrix W, whose entries have the following property. So there are independent entries, centered, so they have mean 0, and their variance, so their second order moment, is simply given by the coefficients of this matrix A, this fixed matrix that we gave ourselves. So this bistochastic matrix, if you want, is what is giving us the variance profile of our random matrix W here. So this random matrix W in particular is going to be very sparse. So everywhere where this matrix A has 0 entries, this matrix W will also have a 0 entry. And on the places where it's not 0, then the variance is given by the value of the matrix A in this entry. And then we also needed like a more technical assumption, which is that we needed to control the growth of the moments of this of the entries of this random matrix W. So we needed to be able to say that the so here the 2p order moment of our random matrix W is upper bounded by something that's scaled as a power of p. So like particular cases of this assumption would be in the case where beta is equal to 0, so you have entries that are almost surely bounded. The case where beta is equal to 1, you have what we call sub-Gaussian entries. The case where beta is equal to 2 would be sub-exponential entries. And we can allow for like heavier tails than this, as long as we have this polynomial control. So it's a quite mild assumption on the distribution. I mean, a lot of distributions have these properties. And then what we did is okay, now let's pick W1 to WD, independent copies of this random matrix W. And then we take as cross operators, so Wi divided by square root of d. And we look at phi, the random CP map that has this random cross operators Ki. And what we showed is that on average, this map is going to be trace preserving, unital, and such that its spectral expansion parameter is upper bounded by this optimal value, so the scaling 1 over square root of d. So if you want, like the whole interest of this was really to show that you can actually construct like a random optimal quantum expanders from any optimal classical expander. So you have this recipe for how to construct this quantum expander from a classical one. And it's also showing that, in fact, so you can obtain optimal quantum expanders from distributions that are much more economical than all the ones that were known before. So before we had like this very full matrices for our cross operators, so these Haar unitaries or these Gaussian matrices. So now what we show is that you can have matrices that are very sparse, these matrices W here, as long as their variance profile is well enough distributed, like according to this matrix A, which is itself a classical expander, and with a distribution of these non-zero entries, which is basically anything that you want, as long as it satisfies this moment growth assumption. And maybe one last comment on this is that, so here I stated things like only on average in order to have like somehow minimal assumptions in the theorem. But of course, if you put more assumptions, you could at least compute variances of these quantities and show that results hold, maybe not with overwhelming probability as in the case of Gaussians, but at least with positive probability. Okay, so I'm really running out of time, so I'm going to completely skip the proof. Because I would really like to spend like 1 minute on telling you what are implications of this result when looking at correlations in many-body quantum systems. I mean, it's really just one slide, and I'm not going to say anything really precise, but just to give you an idea. So when you're looking at many-body quantum systems, so one problem that shows up is that these have a very large dimension. So the dimension of the system grows exponentially with the number of subsystems that you have. And there is a particular subset of many-body quantum states that are known as matrix product states, or MPS, which are particularly interesting because they combine the two following properties. So on the one hand, they are nice from a mathematical point of view, so they admit an efficient description, so they can be described with a number of parameters that scales linearly and not exponentially with the number of subsystems. So they admit this very efficient description, and they can be used in like, say, for instance, ground state computations and things like this. And on the other hand, they are known to be like physically interesting, so they represent states that are actually like interesting states from a physical point of view. In particular, they are known to be good approximations of ground states of gapped local Hamiltonians on 1D quantum systems. So that's a class of state that is particularly interesting. And what we looked at with David Perez Garcia was trying to understand what are typical properties of these matrix product states. And in particular, so what we showed is that if you take a random translation invariant MPS, then typically you can show that it has that the correlations between two subsystems that are far away from each other will decay exponentially fast with the distance separating these two sites, and with a correlation length that you can prove is very small. And the way we showed this is actually by observing that the correlation length of an MPS is actually given by something which is 1 over the absolute value of the log of some spectral expansion parameter lambda of phi of a quantum channel phi that is associated to our MPS and which is called the transfer operator of our MPS. So somehow, if you're able to understanding the spectral gap of this guy, so this transfer operator, you're immediately allowed to understand the decay of correlations inside the corresponding MPS. So that's one place where this thing shows up. And I mean, I will just leave you with some open problems, but I will stop here because my time is over. So thanks.
Thank you very much. Are there questions or comments or remarks?
Yeah, I can speak louder if it helps.
Maybe it's better to use because of the back.
It seems that your work here has applications to finite groups. If you consider a finite group, say with n elements, but with d generators, the Cayley graph is a d-regular graph.
Yes, exactly.
So then the question is, for what type of finite group, the Cayley graph is Ramanujan?
I don't know exactly because I'm not an expert, I mean, of the classical setting and even less of the explicit constructions, but I know that some of the explicit examples that are known in the classical case, so here, yeah, it's based, so you need so I think one thing that you need in order to achieve this optimal spectral expansion is that the group is non-abelian. I mean, so that's, if like with abelian groups, it doesn't work, but then with non-abelian and some extra assumptions, because I mean, for instance, like the constructions work only with this in this very specific, with this very specific degree d, then it does work. But some like these explicit examples, I mean, it's work of like Margulis, and I mean, so. I mean, I could check the references, but so the short answer is I don't know exactly which ones, but I know that some of these explicit constructions are from Cayley graphs of non-abelian groups.
Okay. So a related question is, suppose the group is generated by little g1 up to little gd, okay? And if you have a representation, a unitary representation of that group, you have, say, let's say the representation is pi. So you have a pi of g1 up to pi of gd, and that provides a cross operator.
Well, that's one thing that is not really clear. That's the thing, and that also that, I mean, for instance, in this, like, as I briefly mentioned, I mean, in this first attempts at, like, really somehow, like, putting what was known in the classical case inside the quantum setting, a lot of things failed. So you have some natural ways also of I mean, embedding your I mean, somehow, so, okay, sorry, what I want to say is that, so you do get something that is non-trivial if you try to do this, so you get a spectral gap, but somehow you lose something in the process. Like you don't reach this 1 over square root of d, but maybe some, I know, 1 over d to the 1/4 or something. You reach something else, and even so, with the naive way, it's like with the naive way of doing it, you would go from something, like you would have a graph with degree d would be mapped to a quantum channel with cross rank n times d. So, which is still, I mean, if d is much smaller than n, this is still much smaller than n squared, so you're still doing something non-trivial somehow, but you've really lost something. And then you have ways of improving this by some tweaking, but not of reaching the optimal value, at least up to now, what people have tried to look at.
Okay, thank you. Other questions? If no, we thank again the speaker.
you.